Physics 2211, Lab 3, the black hole. My name is Yuvraj Well. Let's get started. All right, so introduction. The purpose of this lab, we've got three parts. Part one, which is to find the mass of the black hole. Part two is using the mass of the black hole, find the initial velocity of the ship to ensure there's no collisions with the black hole. And then part three, or the what if question, is find the initial velocity for the ship to ensure an orbit around the black hole. Some fundamental principles we'll be going over is Newton's second law of motion and the momentum principle, which is just F net is equal to mass times acceleration. And then we've also got the force of gravity. So a little bit of preview. The mass of the black hole is 1.1 times 10 to the power 34, and the initial velocity of the ship is a grand total of, in the x direction, negative 6.13 times e to the power 6 times 10 to the power 6, and 8.41 times 10 to the power 6 in the y direction. All right, so we've also got the universal gravitation law, which is just Fg is equal to g mass 1 times mass 2 divided by radius squared times the r hat, negative r hat. And we also got magnitude. And we also got Newton's second law and the momentum principle, which is just F net is equal to the change in momentum over the change in time. And we've also got F net, which is got perpendicular and parallel components to it. We got our velocity update and our position update as always. And we're also going to assume for this lab that the net force is equal to the gravitational force. And that is because we are in space. So we are assuming that the only force acting on these objects is the force of gravity from the other objects in the question. And since universal gravitation is a non-constant force, we will be substituting average velocity with final velocity, just because we just can't find average velocity for this. And obviously the changes in parallel force will change the magnitude of force, and changes in perpendicular force will change the direction of the force. All right, and so for part one, we got our systems and our surroundings. Our systems is the star, our surroundings is the black hole. Initial conditions, we got our constant g, which is always the same. Our star mass, which is 2 times 10 to the power 30, and our delta t, which is just the time of 1 day in seconds. And then we're starting at t is equal to 0. So a little bit of code. We, on the left here, you see this block of code. We are just calculating the net force on our little star due to the black hole. And then on the right, you can see we're calculating our parallel force as well as our perpendicular force. And then at the bottom here, we are using our F net to calculate the mass of the black hole. Pretty simple stuff. And here's our results. We found our F net, which is 7.97 times 10 to the power 28. We've got our F parallel, which is 1.4 times 10 to the power 28, and our F perpendicular, which is 7.8 times 10 to the power 28, and our mass of our black hole, which is 1.1 times 10 to the power 34. All right, so for part two, we've got a system, which is a spaceship, and our surroundings, which is the planet and the black hole. Some initial conditions, same thing. We got our constant g, our planet M, which got a mass of 9 times 10 to the power 28, our ship mass, which is 7 times 10 to the power 10, and then our delta t, which is just 1 second. And we are using the exact same mass for a black hole that we calculated in the last part in this part as well. And then we got our initial conditions for the planet, which is already given in the source code. All right, so first step is to calculate our net force acting on our planet, and then the net force acting on a ship. To do this, we've got to find the force acting on the planet due to the black hole and due to the ship. And then you add those two together, we get our force net on our planet, and we do the same thing for the ship. All right, and then we've also got our velocity and position update formulas that we stick in. This is so that we can predict the motion of our planet as well as our ship. As you can see here, here's the graph. We calculated that with an initial speed in the x direction of negative 6.13 times 10 to the power 6, and in the y direction of 8.41 times 10 to the power 6, we are able to escape the grasps of the black hole, and we are all good. All right, so some possible sources of error in this lab is we could have had our program run for a little longer to calculate a more accurate average mass for the black hole. And for part two, I did guess and check a bunch to find the initial velocity, so it might not be the most optimal one. That's just how it is. And we've also got maybe too short of a time interval right now. Maybe later on, our little ship will circle back and hit into the black hole. We're not too sure because I didn't run it for that long. All right, so what does it mean? So the what does it mean question is just asking for what is the difference between the parallel and perpendicular components of the net force and the parallel and perpendicular components of the rate of change of momentum. And these are the exact same things. Actually, it's because the rate of change of momentum is just your net force. That's what we have learned in the momentum principle. It's just a lot easier to find your delta momentum than it is to find your net force. So it's a lot easier to do that. to solve it that way, which is why we've done it in our labs. All right, so the what if question is asking, hey, what are the initial conditions for the ship speed to be able to orbit around the black hole? We found that negative 6.13 times 10 to the power 6 and 8.41 times 10 to the power 6 is able to be the perfect initial velocity to orbit around the black hole. As you can see on the left, we've got a snapshot in time, and at the end, we show the full thing. Perfect. Thank you all for coming, and I'll see you guys next week.